has been a while since I started this series, and this is the video I've been thinking a lot about. The topic of combustion brings with it a lot of subtopics which are quite complicated to explain. Well, it felt like it needs a lot more than usual. So here I am talking to you about.
A boring video about chemistry in OpenFOAM Part 3.
What is combustion? It is more than just heat and light. Microscopically speaking, these are chemical compounds that are involved that undergo species transformations. These are chemical components that undergo rapid transformations, right? Tracking these chemicals is key to simulating flames and high temperature zones. At its heart, combustion is a chemical reaction where combination of fuel and oxidizer spits out products and heat. We need to dive a little deeper here. What exactly are chemical reactions?
Combustion is a chemical reaction which involves a product and a reactant and is generally associated with flames which produce heat and light. A chemical reaction includes consumption or destruction of reactants and production or creation of products. It is as simple as A plus B equals C plus D. Chances are you're not going to get what you started with, but for a combustion reaction, you end up gaining heat and light at the end of it. Studying combustion gives us an insight into this process.
Remember, we are no longer dealing with a single fluid here. We have a fuel and oxidizer which are mixed together. These are products which themselves are multiple species. To understand combustion is to keep track of how the concentration of each species changes. Now, this can happen through certain phenomena, something like convection, diffusion, and chemical reactions. Now, how do we keep track of these things? Mathematics. So we have seen the conservation equations. However, these work just for the bulk fluid. Now, as I said before, we are dealing with a multi-component fluid. To track the individual species, we need a separate equation called the species transport equation. This deals with the conservation equation of mass of each individual species and includes your energy transfer as well.
Alright team, our file has 4 key pieces of evidence we need to analyze. Let's look at them one by one. Clue number 1, the unsteady term. The first thing any good detective asks is what's changing right now. This term is a time of death report. It tells us at a single fixed point in space if the concentration of our species is increasing or decreasing over time. Is our suspect appearing at the scene or vanishing? The transient term is particularly interesting because it represents the net result of all other physical processes, convection, diffusion, reaction, all at a single point in space. Talking about change in a property with respect to time, we have this animation that you can see here. Essentially what's happening here is in the middle we have a hot region inside which fuel turns into your reactants, explaining how this is time dependent as much as it is about movement as well. Thing to remember about this term is it's not a physical process itself, but rather the final result you see after all other transport effects have combined. Clue number 2, convection. A species doesn't just stay in one place, it gets moved. This is convection. Think of this as the getaway vehicle. It's the bulk flow of the gas the wind carrying molecules away from the crime scene on the main highway. If a large group of molecules moves from point A to point B, convection is responsible.
Species are carried along by the bulk movement of fluid. It is governed by the fluid velocity field U, as you can see here. If the fluid moves fast, the species move fast with it. The convection term represents net flow of a species out of a tiny volume due to fluid's velocity.
As we can see in this animation, we have just the particles moving in the directions left, right, bottom, up, and even diagonal. This is what the convection term essentially is. It's the term responsible for large-scale transport that creates the beautiful swirling patterns. Clue number 3, diffusion. But molecules don't just follow the highway, they have their own agenda. This is diffusion. It's our suspect slipping away from the main road, blending into a crowd. Molecules naturally move from an area where there's a lot of them to where there are fewer, from high concentration to low concentration. It's a much more subtle, random, and local kind of movement. As can be seen in this animation, we have just the diffusion or spread of our particles. However, diffusion is associated with molecular motion much more. It represents the net movement of a species from an area of high concentration to lower concentration. It's largely driven by these random molecular motion. This is a physical process that causes the sharp edges of our dye plumes to blur, to spread out and fade over time. And finally, clue number 4, the smoking gun, so to speak, the source term. This is where the action happens. The first 3 clues were about movement. This one is about transformation. This is the chemical reaction itself. This term tells us if a species is being created out of other molecules or if it's being destroyed to create something new. This is the DNA evidence, the fingerprint that proves a reaction took place right here, right now.
Wait, why are we tracking them again? Well, reactions happen where reactants meet. We need to understand where fuel is meeting oxygen to ascertain the likelihood of having a flame. This heat release is completely dependent on how quickly your reaction is occurring. This is called the reaction rate. This consumption rate of these two compounds, of your reactants and oxidants, essentially determines the resultant temperature.
Simulations can help understand what exactly is happening within your domain when it comes to combustion. We get great insights into having a good way of measuring every single point in space and time to understand what's really happening within the domain. For instance, how your carbon dioxide is getting created or how your methane is being consumed at every single point wherever you choose to measure it. This gives a great way for us to understand how exactly is my combustion occurring and whether or not it actually matches my experimental data.
Temperature drives just about everything. High temperature changes the fluid density, which affects the fluid flow itself. Now, the products tell a different story altogether, where we need to keep track of, let's say, CO2, H2O, but also pollutants like carbon monoxide, nitrous oxides, and sulfates and whatnot. Simulating this phenomena essentially means each chemical species at every point in space and time needs to be tracked as accurately as possible. Species transport helps answer these questions. Where do species come from? Where do they go? Where did you come from? Hot and Night Joe. We want to understand how they move around, how they are created. Add a video of stuff coming out of burner, inlets, and outlets. Wait, am I supposed? Species are consumed or generated according to the chemical reactions. This is fully governed by the temperature, the pressure, and the concentration of our species, usually governed by something like the Arrhenius law.
So the way OpenFOAM does it is a bit different depending on which version of OpenFOAM you're using. The one that I use is generally OpenFOAM version 12 from .org. You could use the openfoam.com. The current version is 2412. They should very soon come up with 2506 as well. Coming back to the point, this code is essentially from family of solvers designed for reacting flows, specifically reacting foam, etc. The thermophysical predictor, this is a core part of the Pimple Piezo algorithm, which is a predictor corrector step. Essentially, this speaks about first you make a highly educated guess about what the new species concentrations and temperatures will be, and then you correct it in that you use this guess to update the pressure and velocity and then come back to correct its initial predictions until the solution is consistent. Now, the goal of this function essentially is to make the first official guess for the outcome of the next time step. It has two primary objectives. The first is to solve the species transport equation for every quote-unquote person of interest or yi, and at the same time solve the energy equation to determine the new temperature of the quote-unquote crime scene. The first part that we see here, so before the main investigation, the code essentially does two setup tasks. First, it helps create a helper object. This is the MV convection that knows how to calculate the convection term based on schemes defined by the user in FV schemes file. Second, it calls the reaction correct. This is crucial. It essentially updates all the chemical reaction rates based on the current temperature and composition of the fluid. Next, we have the part 2. This is the main event for species transport, so to speak. The code loops through every single species and solves its transport equation individually. The code starts to loop for every species if the if statement is a simple check. Are we actively solving for this species? Usually yes, but you could freeze a species for certain simulations. At the same time, the FV scalar matrix, this is the absolute core. The code essentially builds this matrix equation that represents the discretized species transport equation for the current species, yi. Each line corresponds perfectly to a term in the theoretical equation. The first term, you can see this is the unsteady term, or quote-unquote our time of death report. How is concentration of this species changing at this very moment? Next, we have the convection term. This is the getaway vehicle. How is the bulk flow of the gas carrying our suspect away? Then we have the diffusion term. Our suspect is slipping into the crowd. This term represents the molecular diffusion flux, J. It's a more complex term that accounts for how species diffuse due to concentration gradients. And ultimately, you have your yi. This is the smoking gun, the source term. This is the quote-unquote DNA evidence. This calls our chemical forensics expert to calculate how much of the species is being created or destroyed by the chemical reactions. Ultimately, we have an additional source term for other physics also incorporated, something like the spray evaporation. Generally, for a simple gas flame, this is often set to 0. Now we have the solving part. this is where we see that the under relaxation is also applied. This is for a numerical stability, a trick that essentially prevents the solution from changing too drastically within one iteration, which could also cause the simulation to blow up. The command here, the yi equation solve, is to solve the assembled equation ax is equal to b to find the new predicted value for our yi field. And at the same time, you have any of your user defined constraints like ensuring that a certain species fraction doesn't go below 0, etc. also applied right here. Now we have the final head count and energy investigation, so to speak. The normalize is essentially you want to implement a crucial cleanup step where, due to small numerical errors, the mass fraction of all species might not add up to exactly 1.0 anymore. This function corrects them so they do. The FV scalar matrix E equation, just like for the species, it assembles and solves a big matrix equation, but this time for energy, often in the form of sensible enthalpy, HE. The terms on the left, TDT, DIV, track how energy moves around via convection and diffusion. The most important term on the right is reaction arrow Q dot. This is heat released or absorbed by the chemical reactions, the heat from our smoking gun. After solving for the new equation, this function is called to update all other temperature dependent properties like density, viscosity, based on this new predicted temperature. So there you have it. This is the species transport equation implemented in OpenFOAM.
This is the actual combustion part. It links the dynamics of the fluid to the chemical transformations of the heat release. This term is calculated by the combustion models like these displayed on the screen right now. Add a simple reaction diagram with reactants consumed and products created. Wait, am I supposed to say this?
So what you are seeing here is the chemical species involved in the reaction. This is the GREMEC 30 or the mechanism for combustion of methane. As you can see, the arrows, these represent the transformation of one species into another, and the thickness of this arrow matters a lot. The thicker the arrow means faster, more dominant reaction, and vice versa. At the same time, the numbers on the arrow, these represent the elemental flux. This is the numbers changing on top, essentially explain how quickly your reaction is occurring. Now on the bottom you will see there is something called scale. This is an invented number that we have created to explain how quickly this reaction is occurring. But as time increases, you can see what's happening to the reaction mechanism.
Combustion modeling helps understand how flow field influences convection diffusion of your individual species. Species concentration and temperature helps determine the reaction rates. Well, reaction rates define the consumption and production rates, and hence the release rate of your heat, which again changes the temperature. It's a convoluted loop of sort where ultimately your flow field is influenced by the temperature, and then the flow field in itself influences and increases your temperature locally. Species transport helps predict flame location and its structure. It helps determine the temperature distribution as well. It calculates your pollutant formulation too, helps assess combustion efficiency with understanding of how the fuel is burnt. To be fair, learning combustion is all about design and optimization of devices such as your burners, like your furnaces, and much more. In the next video, we'll talk some more about combustion and OpenFOAM. Until then, you can check out some fast. In the next video, we'll talk some more combustion and OpenFOAM. Till then, I have made a few videos about combustion. You can check them out right there. So until next time, thank you.